Hi, good afternoon. My name is Navab Singh. I'm from A STAR Institute of Microelectronics, Singapore. We have established an 8-inch silicon carbide line and qualified that with various platforms. So in this talk, I would be introducing the capabilities in our silicon carbide line, as well as the platform technologies we have developed and our focus moving forward. The outline of my talk will start with introduction of A STAR, followed by silicon carbide, the material of choice for power electronics, and our play in that silicon carbide power. That will be followed by major challenge with silicon carbide power MOSFET development, and that would be the highlight of my talk, how we have addressed and how we are addressing those challenges, right? And then I will update the status of the line with key capabilities, followed by our future directions, and then I would summarize the talk. Let me start with introduction to A STAR. A STAR is Agency for Science, Technology, and Research, a RTO in Singapore. A STAR consists of 17 research institutions, 9 research institutions under biomedical, and 8 research institutions under science and engineering. The total strength of A STAR is 6,000 plus. Out of those, about 4,700 are researchers and technologists, and they are coming from more than 60 countries. So we are a very international organization. Under SERC, Science and Engineering, we have 8 research institutions, and I have shown here the name of 4 research institutions which are working in semiconductors. Institute of Microelectronics, IME, is absolutely semiconductors. Everything is semiconductors. And other 3 research institutes are partly in semiconductors, and we are working together under same umbrella. So the total strength of the semiconductor people under A STAR is 500 plus. That's how IME look like. We founded IME in 1991, having a clean room area of 8,000 square meters today. By the end of next year, we are adding another 7,000 square meter clean room area, and that's, I think, 6,000. Then we will be 14,000 square meter end of next year, expanding our 12-inch operations. Today we are, 40% of that is 12-inch. We have 6-inch line, we have 8-inch line, and 12-inch line, with 40% 12-inch, and we are expanding 12-inch, right? We are 300 people within IME and 200 coming from our sister institute to make it 500. With 65% of those research staff. Our focus, major focus is not publications, but we still publish about 200 papers in a year. These are the programs you can see at IME, starting from advanced packaging, which is considered our adult program running in IME for last 15 years with very high intensity. Then we have other programs, MEMS, where our focus is piezo MEMS. And we have established a lab-in fab for piezo MEMS in ST Micro Fab, which is a public domain information, and you can Google it. Then we have other high-intensity program, advanced photonics, where we had indeed in 2017 a spin-off from IME, Advanced Micro Foundry, which is focused on silicon. And today we are working on next-generation materials like lithium niobate, 3,5 indium phosphide, etc., to integrate those on silicon wafer, on 12-inch silicon wafer. The next is silicon carbide, which I will be presenting today. And then we also have active programs in RF GaN, where we are working on 8-inch GaN on silicon for high power, high frequency, and also, 6-inch GaN on silicon carbide for high power, and 8-inch GaN on silicon for relatively lower power, but still higher frequency. And then we also have a team on high performance integrated circuits. Let me move into the material properties. If you look at on the left the spiral diagram, which tells the silicon carbide is a superior material. The most important property of the silicon carbide, which is making it a superior material for power electronics, is its breakdown field. Its breakdown field is about 10 times higher than silicon. That allows the drift layer in power device to be shrinked by 10x, and the doping level to be increased by at least 2 orders of magnitude, making almost 1,000 times improvement in drift layer resistance. There are other issues which need to be sorted out, but drift layer resistance can be very significantly reduced. The material is having very, very high thermal conductivity, which is allowing this material to shrink the device. Means your power density is very high, heat can be extracted. If it is silicon or if gallium nitride or other materials, it's very hard to extract the heat, but in case of silicon carbide, you can easily extract the heat. On the right are shown the applications of power. Indeed, if you look at any electronic device, there are always power converters. There is power management, there are power converters. Almost maybe more than 50% of the power generated today, utilized today in electronics and electrical equipment, the 50% is going through the power converters. And silicon carbide provide the high voltage, high power converters in these applications listed here. And you can see at the bottom, the market is growing very fast. This is Yole report 2025, and 2024, sorry, and it's published in August 2024. And you can see here the silicon carbide market in total was 10%, which is growing to 25% in next couple of years, next 4 years, right? It will grow very fast. And GaN is also growing, but GaN is only a very small percentage of silicon carbide. Although GaN is going into 12-inch, the wafer size is growing, and silicon carbide, so wafer size may also grow, but today it's 8-inch, and it may stay for a couple of years at 8-inch. This is our play. IME is active from silicon carbide epitaxy to system demonstrations. So we have epitaxy, process module, integration, chip design, test characterization, reliability failure analysis, and power module package. In power module package, we are looking at shrinking the size of the power module, looking at DVC-free options, double-side cool options. Let me talk about the major challenge in silicon carbide, and which has been our focus. So one of the major challenges in silicon carbide is poor MOS interface. Our line, let me say again, our line is a MOSFET line, making transistors, right? The MOS transistor require very good quality MOS interface. Silicon carbide, because of the presence of carbon as compared to silicon. Silicon, the MOS interface is perfect, nearly perfect, right? You can see the DIT values are in E9, maybe high E9. In case of silicon carbide, if you just oxidize, the DIT values are, the interface track charge values are in E13, right? It's about at least 3 orders of magnitude higher than silicon, just because the carbon coming out of the silicon carbide matrix is creating problem. To control that, people had optimized and utilized different kind of post-oxidation anneal. People have used not only the grown oxide, also the deposited oxide, and anneal that in NO, N2O, N2 at different temperatures, and try to control these DIT values. And there is a very clear impact. You can see here the DIT impact on mobility. So the channel mobilities, if you don't pay good attention, if you don't have the know-how, your channel mobilities may be 10 to 15 centimeters square per volt second, right? It can be as bad as that. While in the bulk mobility in silicon carbide is 1,000 plus. right? That's not the case with silicon. So that means it requires a lot of engineering, and because of that, you can see the channel resistance, the right side figure, the channel resistance, especially for low voltage devices, and when I say low here is up to 1200 volt, which is for EVs, right? Up to 1200 volt devices, the channel resistance is a significant part of the total resistance, and one needs to really improve that to have high efficient power conversion. The another issue is the bias temperature instability. The threshold voltage shifts. When people solve this problem of interface by NOPOA or N2POA or N2OPOA, there is a damage in the oxide. And that damage in the oxide is generating to traps, and those traps are capturing carriers and thus shifting the threshold voltage as explained by Agarwal et al. In the bottom graph. The another problem in silicon carbide is the defect, the extended crystal defect in substrate. That is start from the substrate and propagate into the epitaxial layer. Epitaxial layer is to provide the device layer actually on a carrier substrate. And if you don't do the epitaxy well, if you don't have the know-how of the epitaxy, you end up having a crappy epitaxy layer, the device layer, which has a lot of extended defect, particularly the BPD, the basal plane defects, which are huge reliability concerns. They expand once you stress the body diode, they expand into Shockley stacking fault, and that results in increase in the body diode resistance, increase in your RON, and also create problem in the leakage current. And for that, one has to have a lot of know-how in how to start the epitaxy growth, right? To convert these BPDs coming from the substrate to TDs. And that conversion has a lot of tricks. Otherwise, you can see on the bottom left, the graph which is showing after stressing, there's a lot of stacking fault generation. Let me talk about the status. This is the status of our line. We have, besides epitaxy, the implantation where our core is to apply channeling implant. Silicon industry was running away from channeling, was finding solutions, right? Having tilted implant at 4 degree, at 7 degree, different angles to avoid channeling. Silicon carbide in the past never utilized channeling, but recently you can see a lot of publications coming out of channeling, and we have implemented channeling in our line. And for implementation of the channeling, we have collaborated with Nissin, who is having an integrated XRD so that we can put the ions correctly inside the pores in the right channels. For the trench, you can see here we have developed a trench which is very rounded corner. For the interface, we have optimized the process such that our interface is extremely sharp, and not only a conventional planar or trench gate MOSFET, we are also developing superjunction MOSFETs, and for that we had developed a very, very innovative alignment scheme, and you can see here the columns are aligned under lithography category very nicely. Then power, and now we are ready to work with our customers with a focus into the trench, fin, and superjunctions. Let me talk a little bit more about epitaxy. I said we need very, very low defect density in epitaxy. I'm not talking point defect, but extended defect has to be very low. Point defects will play with the carrier lifetime, and that's a second order problem. At first, you should have very, very low extended defects. What you can see here in the top graph, bar graph, right, the blue is our qualification of the tool, right? And from there, we started developing, improving our process, and you can see that we have finally developed a process which is having a defect count of better than 0.4 per centimeter square, and including all the critical defect put together, which is one of the best-in-class epitaxy today for 150 as well as for 200 millimeter silicon carbide. At the same time, we implemented AI machine learning for improving the thickness and doping uniformities. You look at the top left, the graph here, which shows our uniformity, the thickness uniformity. 1 sigma uniformity is better than 1, so 3 sigma is about 3%. I would say this is best-in-class thickness uniformity for silicon carbide. And here are some of the details of AI machine learning implementation. You can see at the bottom that we run 15 experiments, 15 DOE using the expert knowledge, supported by 32 DOEs, guided by the AI machine learning. And with the help of that, we improved uniformity from 6% to 3%, absolutely 100% gain. Now we are implementing physics-based models with this AI machine learning and trying to improve further. And that's not only for the epitaxy, but now we are implementing this AI machine learning for all process modules in A STAR. Let me talk about the industrial grade process module. The implantation, I talked already that we have this Nissan implanter in-house with XRD integrated, and this is able to channel phosphorus, nitrogen, aluminum, depending upon their doping concentration. Yes, this is one of the very, very key developments. You look on the left, particularly pay attention to the TM, high resolution TM and yields pictures. The interface with a conventional way of doing oxidation, NOPOA, or even deposition is very, very blurred. By doing a post-treatment, we have recovered the interface to absolutely very sharp. You can see there is no oxygen now in the silicon carbide using our approach. And that is able to solve the BTI problem. Clearly, there is a 10x improvement in PBTI here, and similar improvement is shown in NBTI. So we will have with this process very good mobility along with good BTI performance. This is just the DIT extraction, and you can see on the left side we have gotten a DIT which is about 2E11 or 3E11, and the predicted mobility from here is about 55, which is at least 3 times better than what people talk on the product devices. The process we are using here is very different from you may find in some research papers where people are just using some ways to improve which are not manufacturable. But when we develop the technology, we are very much focusing into manufacturability. We are very much focusing into simplicity so that cost is low, and we are going to get good mobility with simplicity and low cost. MOSFET demonstrations, we fabricated planar devices. We started indeed with planar devices to confirm that our process modules are in good shape, because planar device is relatively simple. And here is just an example of a planar IV characteristics and a breakdown characteristic. So on and off characteristics are both obtained in the same device. And our simulation models are so close. You can see here the real breakdown is 1460 while it was simulated at 1485. It's absolutely very close. At the same time, as test vehicle, we put many, many small devices inside to understand the process uniformity. If you make a big device, you don't know. You get the averaging effect. We put many, many small devices to understand how the VT, how the hysteresis, etc. are varying. And you can see here the very tight distribution for both VT and hysteresis, which tells our process is very, very good. Let me talk about the future directions. The industry is moving towards the transgate from planar. The reason is very simple. You can see here in the top left. When you scale down the cell density, you are shrinking the transistor. Your JFET region is becoming smaller and smaller. At one point of time, JFET region is completely pinched off and making this resistance very high. Device is not feasible anymore. You cannot turn on this device when JFET region is completely pinched off. While in case of trench gate, you can keep on scaling. As long as your lithography, as long as you have good contact, you can scale the size of device and you can keep reducing on resistance. And on the right side, you can see that is not only for the on resistance, which is Balga's figure of merit, but also the high frequency performance of the trench devices are better because its charge behavior is better, its QZ is smaller. Let me talk a little bit here about the process module which are key for trench gate. The very important process module is the etching process for the trench. And you can see on the top right, we started our process from the left, right, then we did some treatment and we obtained the centerpiece. And with center trench shape, we fabricated a full device, we characterized device which is functioning, which is not, I wouldn't call this a ideal, this is not a great device, but it's functioning, so we're styling. Our integration flow is good. But in the meantime, we improved our etch process. And what you see on the right side is our etch process with bottom completely rounded. You can fit a tube inside this channel. This is best for breakdown. You will have no field crowding because of the corners in the trench. This is our readiness for fin device. We have a scanner which can resolve down to 110 nanometer on transparent silicon carbide wafer. That means we can have a fin density of 110 and 110 is 220. We had demonstrated here 300 nanometer is 150 and 150. That means our lithography is fully ready for fin type devices, and on the right bottom is the implant scheme. We had done the column formation for a superjunction using implant epitaxy, and for that we had developed an alignment mark. The problem of industry today, if you have an alignment mark which is having a topography in silicon carbide, you just cannot keep that alignment mark safe during the epitaxy. Silicon carbide epitaxy will make it, distorted. And this alignment mark will not work. Other material does not survive at epitaxy temperature, which is 1600 plus degrees centigrade, right? So how to make this alignment mark is really a key innovation here, and we had done it. We have obtained 12 micron thick column with single alignment mark. It's not repeated at all. Is the summary? So we have the line ready. We have established all the process modules. We have integrated the process modules in platforms. We have good class or epitaxy with very high speed. Deposition speed is 50 micron per hour. So this is not only for 1200 volts, but tomorrow if we are driving to very high voltage, this epitaxy can grow very low defect material up to 100 micron very easily. It's a single wafer chamber. We have good MOS interface. We had demonstrated planar devices, trench devices, and process module for future devices, FinFET, and super junctions. That way we are ready with the platform to have deeper engagement with industry. We already have it, but we invite you all to work with us in silicon carbide. Thank you very much.
Now it's open for discussion. Any questions?
And thanks for your nice talk. And I have two questions. The first one is that can you tell me the RNSP for your 1.2 kV device, the current latest RNSP?
Currently, the RNSP for our current device, which is a planar device, is about 4 milliohm centimeter square. The reason is we had not scaled the device from the design. Our focus has been on the process modules, so getting the process module right. So by chip scaling, by design scaling, the cell pitch scaling, we can shrink that. So that's not a problem for us.
Thank you. Yeah. And another question is that I find you have one amazing FinFET structure. Yeah, and can you talk us more about its performance and some technical challenges when fabricating the silicon carbide FinFET device? Yeah, thank you.
I would say the challenges, technical challenges in FinFET device is, number one is when we are etching the fin, we have to be, we have to have an etch process which is quite selective to the hard mask, because hard mask material is limited. With high resolution patterning, you cannot use thick resist mask for thick hard mask, which is generally used for trench fabrication, right? You may have noticed that the hard mask used for trench gate is about 2 micron, which is pretty thick. But for fin, we have to use very, very thin. Another is the contact resistance. We have to make a good contact, right? Will this contact be directly to the fin, or will this contact require some kind of, other epitaxial growth on the fin top? Those are things to be investigated.
Okay, thank you.
Actually, I have one.
Yeah, sure.
And we want to know, for example, A STAR is like a government-sponsored research institute, right?
That's right.
So if you have partners, they want to bring their products into production, is there any?
Then yes. So we do R&D and prototyping for our partners, and for manufacturing, then we work with high-volume manufacturing partners within Singapore and outside Singapore. We are open to work anywhere.
Okay, thank you.